Okay, hello everybody. At the moment, 1 plus 1. Yeah, this is minimum for a while. So, I would like to start with continuation. So, as far as I remember, that is about 12.2, continuation. So we'll continue the section from yesterday, and let me recall what it was about. We considered area of surface for solid of revolution. So we have y equals to f of x. We rotate it about x-axis, and we want to compute the area of surface for the resulting solid and in last lecture we replaced our solid of revolution by frustum. Better to say union of several frustum, and the total area of that frustums together was equal to pi sum k from 1 up to n yk minus 1 plus yk times square root of xk minus xk minus 1 squared plus yk f of xk minus f of xk minus 1 squared. That is so one term in that sum is the area of the surface of this thin frustum. And also we replaced yesterday we replaced it by f of xk minus 1 plus f of xk. I replaced it by this, then square root of 1 plus f prime at psi k squared delta xk. And what I want to prove, so let us prove that limit as norm of partition tends to 0 for the difference between this sum and integral sum for the function g of x, which is equal to f of x square root of 1 plus f prime of x squared. This function also was introduced during last lecture, and I want to prove that this limit tends to 0. So the difference between area of surface for this solid which consists of several frustums, is close to integral sum for that function. So, proof. So this is claim, right? That is claim. That is claim. Proof for that claim. We write down the integral sum for the function g, and that will be 2 pi sum. Oh, sorry. 2 pi should be 2 pi somewhere. 2 pi, and then let it be here. 2 pi times this. 2 pi sum k from 1 up to n, and we substitute into our function points psi k and write down that integral sum. So you see, this is the integral sum for that function times 2 pi, and Sp is written here. So what is the difference? Let me estimate the difference between those expressions. So what is it? That is equal to 2 pi times sum k from 1 up to n. And you see, those terms are the same, but other terms are different. So I'll put common terms outside of brackets, and what will be in brackets? F of x k plus f of x k minus 1 over 2 minus f of psi k times square root of 1 plus f prime of psi k squared times delta xk. Now, so I want to estimate that difference, and let us suppose this supposition should be given, of course, from the very beginning. So for f, which belongs to C1 of AB, i.e. f and f prime are continuous on AB. So we'll prove it for continuously differentiable functions. So once f prime is continuous, denote m equals to supremum for f prime for the interval AB. It exists, this is finite number. Why? Because of Weierstrass theorem by Weierstrass theorem that every continuous function on an interval is bounded. F prime is continuous, hence it is bounded by Weierstrass theorem. Now, what we'll do, we we have to use also uniform continuity. So f is continuous on AB, hence by counter theorem says that f is uniformly continuous. On AB. And what it means? It means that for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all, let's say, x and t in AB, which satisfy the inequality modulo x minus t less than delta, we have inequality f of x minus f of t is arbitrarily small, and I want it to be smaller than epsilon over okay, 2 pi square root of 1 plus m squared and b minus 8. That is, let us put it into the estimation for uniform continuity. Okay, then look how we can proceed. Now, for arbitrary p such that norm of this partition is less than delta, and for arbitrary, not xi are not arbitrary, sorry, xi were chosen in special way by Lagrange theorem, they were chosen. So we proceed as follows. Let's estimate like less or equal than 2 pi times sum k from 1 up to n. Then I'll put modulus inside f of x k minus f of xi k plus f of x k minus 1 minus f of xi k over 2 times square root of 1 plus m squared times delta xk. Now, look. So what I did, I estimated f prime by capital M, and also I used triangle inequality, modulo of sum less or equal to sum of modulus, and put it into two terms. Okay, then now look, if norm of our partition is less than delta, what it means? It means that when we consider our intervals, right, length of each of those intervals is less than delta. Because what is norm of partition? Maximal of all lengths of small intervals. What is lambda of p? Lambda of p. Maximum of all lengths of small intervals, right? So, each of them has length less than delta, right? Now, look, both points xk and xik lie on the same interval. So, xik, xk lie on the same interval, right? So it means the distance between psi k and xk is for sure less than delta, right? And it means that we may take xk and psi k as x and t here. The length is less than delta, right? Then what? We know the difference between values of function is less than this number. And same estimate can be applied for the second term. So we have two equal estimates. So divide by 2, it means we have just one estimate. So I put like that, less than 2 pi times sum k from 1 up to n, epsilon over 2 pi square root of 1 plus m squared times b minus a, that is estimate for this fraction, then times square root of 1 plus m squared delta xk. So we cancel those. And what remains? Sum of delta xk. And sum of delta xk is equal to b minus a, right? So cancel with this. And that is epsilon. So look, I took arbitrary epsilon greater than 0, and we indicate delta greater than 0 such that for all distributions, and for all distributions, what we have this limit is equal to 0, right? So claim is proved. Claim is proved. And why it is interesting for us? Because as we know, limit as norm of partition tends to 0 of integral sums for such a continuous function is equal to the integral. So 2 pi integral from a to b f of x square root of 1 plus f prime of x squared dx. So it means that what we obtained is, that is formula for surface area of the solid of revolution. So I didn't prove that formula in full generality because I have no definition of area surface, a good definition. So I refer to some approximate things, including, so you see, here I used area of surface of frosting. I refer to that formula, and we deduce the formula for the surface area, but of course, you see, why this is surface of area if there is no definition? It's a little bit strange, right? But we accept for a while this as a correct formula, and in fact it works. Okay, that is what I wanted to finish, what was started during last lecture. So now let us start another topic. In fact, that is a different section, but still on the same chapter. about definite integrals. Now we'll discuss improper integrals. So, section 13.1. I'll start now. (13.1) Improper integrals. So, what it means, and in fact, today we'll start with just definitions to understand what we are talking about. So, suppose f is integrable on a b for all b a less than b less than capital B. Capital B might be infinity as well, or a finite number, doesn't matter. So I'll write like that. So the function is integrable on an arbitrary closed interval, which lies inside our interval a capital B. Then integral from a to b f of x dx is called an improper integral. Of course, there are two main situations, there are two types of improper integrals. First one is when b equals to plus infinity. And the second one, b is finite, but f is unbounded on a b. These are two types of improper integrals. And for other cases, I mean, for example, if f is bounded, okay, it might be that f is integrable on this interval or not. And but we'll consider mainly those two types. Other types are not interesting for us. So maybe I'll start with just a minute, maybe also let me say also a few words analogously. we define improper integrals for f in, let's say, AB for all A, capital A less than B, A greater or equal minus infinity, and the question is, okay, this, for a while, what was written is just a symbol, nothing else, right? There is no notion. I wrote something and I said, this is called improper integrals. You may ask, okay, you wrote some crazy symbol. Why? Of course, we should think about the sense, right? So, this writing can be written in any of those cases. And then next question, if there is any sense behind it. What I mean by sense, so we say the improper integral, let's start with this, converges if the limit b tends to capital B, okay, minus naught, integral from a to b little f of x dx, exists and it is finite. So, you see, for the first type, the limit as b tends to plus infinity is equal to this integral. For the second type, we have limit as b tends to b minus naught, a to b, or b minus, I forget, maybe b minus we used, f of x dx, that is integral from a to capital B, f of x dx. So, if f, little f, is unbounded near capital B, unbounded, then we consider such one-sided limit, or if we are talking about integral up to plus infinity, then we consider this limit. So, once again, we can write this symbol once our function is integrable for every closed interval which lies inside. No other suppositions. We write this symbol. Then what is the sense? If there exists such a limit, then this limit is precisely our integral, improper integral, right? If not, then it doesn't exist, right? But nevertheless, I wrote some symbol, right? So, but it doesn't exist. So it's a little bit strange. That is why I prefer to use words converges. Converges, right? So you can write the integral even if such a limit doesn't exist, right? It means integral diverges. So if it doesn't converge, then it diverges. So if an improper integral doesn't converge, it is divergent or diverges. So you see, when I write integral and I say it is divergent, what it means? It means there is no sense behind this notation, right? But nevertheless, the symbol is written. So that is why I prefer to call an improper integral just a notation without any sense behind it. And when we are talking about a sense, that is about convergence. And okay, let's start with a couple examples. Example 1. Consider integral from 0 to 1 dx over x power alpha. Look, this is integral of the second type, but for this case. Why? Because the problem is near 0, right? So the function for alpha positive is unbounded near 0. So it means this improper integral, that is improper integral because our function 1 over x power alpha is integrable on a1 for all a between 0 and 1. So it means I can write this improper integral. Now, what is it? What is the sense behind it? The sense, okay, I should write limit as a tends to 0 plus, integral from a to 1 dx over x power alpha. We know what is this integral, so limit as a tends to 0 plus of what? It is either x power minus alpha plus 1 over minus alpha plus 1, substitution from a to 1 for alpha not equals to 1, and logarithm x is alpha equals to 1. Just computing the integral. Then we proceed as limit as a tends to 0 plus, okay, just compute 1 over 1 minus alpha minus a to the power 1 minus alpha over 1 minus alpha. If alpha not equals to 1, limit of this. And here we have minus logarithm modulo a if alpha equals to 1. Then what we obtain? Look, a tends to 0. Then if exponent is positive, right? What will happen? Tends to 0, right? So there is a finite limit 1 over 1 minus alpha for alpha less than 1. Exponent is positive then. But if exponent is negative, it cannot be 0, right? If exponent is negative, then what happens? Negative, negative, minus, so this is plus, and this tends to infinity, right? So we have infinity for alpha greater than 1. And look at the last line. If alpha is equal to 1, logarithm a tends to minus infinity. We have minus here, so plus infinity as well, so greater or equal than 1, right? So what it means? It means that our improper integral, so answer, converges if alpha less than 1, diverges if alpha greater or equal than 1. And let me emphasize, look, that is in fact the main thing which is interested for us in this section. I am not very interested in concrete value of this integral. Of course, for applications it can be interesting, but in this section we'll consider mainly the question if it has a sense. That is the main question, if it has a sense or not. Computing, it's another story. Also, what is interesting for us, look, if alpha is negative or 0, what happens? Alpha negative or 0? Then it means that in fact we have x power positive exponent, right? X power minus alpha, where minus alpha is positive if alpha is negative, right? And it means the function is bounded, and in fact it is continuous even, right? For 0, 1, if I write it as x power minus alpha and minus alpha is positive. So at 0 it is 0, right? Then it is continuous. Hence this integral is a usual Riemann integral, or what is called now, to distinguish with improper integral, proper integral. So for alpha which is less or equal to 0, this is in fact proper integral. But of course the value is the same, right? And it is always, look, if f is integrable for the interval a capital B, or like here for capital A, B, then we can talk about usual Riemann integral, right? Usual Riemann integral. Proper integral. Proper integral. So we don't need to even ask a question about convergence and divergence. This will be proper integral. But nevertheless, you see, the question was stated from the beginning as a question about improper integral, right? So firstly it was written like improper, then we discovered that for alpha less or equal to 0 it can be treated as a proper integral. But also you can say converges if alpha less than 1 and diverges if alpha greater or equal to 1. So you see, sometimes people say for alpha less or equal to 0, it's wrong to say it is convergent. You should say this is proper integral. Unfortunately, here it depends on people. So somebody prefers to think about such integrals for alpha less or equal to 0 as proper integral, not improper at all. Other include to this case and say it's convergent. So it depends on taste, I would say. Okay, let's have a break. Yeah, roughly speaking, there is a question that alpha less than 0 is proper because that x will go in the numerator. Roughly speaking, it's true. Because 1 over x power alpha has a removable discontinuity, right? At 0. 1 over x power alpha, it is not defined at 0, right? But it has a removable singularity, a removable discontinuity point, right? Because you can define the function to be 0 at 0, and then it will be continuous for alpha less or equal to 0. So, indeed, in this case, it will be proper. Okay, example 2, same function, but it will be with different answer. Example 2, integral from 1 up to infinity dx over x power alpha. Since now we have plus infinity, it will be always improper, right? For sure. No such possibility that it might be proper for some values of alpha, no. Once again, we proceed in the same manner, similar, better to say, right? Now we consider the limit as b tends to plus infinity from 1 to b dx over x power alpha. That is limit as b tends to plus infinity. Let me write down the same result from 1 up to b now. For alpha not equals to 1, logarithm x from 1 to b if alpha equals to 1. There is limit as b tends to plus infinity b to the power 1 minus alpha over 1 minus alpha minus 1 over 1 minus alpha for alpha not equals to 1, and logarithm b if alpha equals to 1. Now, when this limit will be finite, look at this. If exponent is negative, then this limit is 0. If b tends to plus infinity, so b is large, then for exponent negative we have limit equals to 0. So I can write that the limit will be 1 over alpha minus 1 for negative exponent, and it means alpha greater than 1. And if alpha less than 1, then we have positive exponent. B tends to plus infinity, so this will be infinity. So we have infinity for alpha negative. And also for alpha equals to 1, logarithm tends to infinity as well, right? So alpha less or equal to 1. Oh, I'm sorry, I forget that usually we don't use plus, right? Okay, let it be plus. I started to use plus, let it be plus. So, you see, quite different. So answer here is answer for the behavior of our improper integral converges if alpha greater than 1, diverges if alpha less or equal to 1. So you see, in some sense, opposite answer, right? So that is a very important example. Why it is important? Because of a possibility to compare. What means to compare? Let me explain. So, first of all, maybe to finish with examples before to start the next one. So, look at this. This is not an improper integral in the sense of any of definitions which were given before. Why? Because 1 over x power alpha is integrable for arbitrary AB, right? For arbitrary interval strictly between 0 and infinity, we can integrate without any problem, right? So it means we have two problems simultaneously here. 0 at infinity and infinity, right? Moreover, it may happen in general. So in general, most general type of improper integrals, let's say integral from minus infinity to infinity f of x dx, where f is unbounded in neighborhoods of, let's say, x1, so on, xm. Then what we can do? By definition, this integral is a notation for the sum of those objects. Of course, you can ask me what means sum of objects if they need not to be exist, right? So the answer is, we suppose the sum of several objects exists if and only if each of them exists and are finite. Otherwise, it can be a problem. So x1 x1 plus x2 over 2. Okay, I forget to suppose this. Finitely many, let us suppose they are arranged in increasing order, plus integral x1 plus x2 over 2 up to x2 plus so on, plus integral from x n minus 1 plus xn over 2 up to xn plus integral from xn up to plus infinity f of x dx. So you see, if we have finitely many points where our function is unbounded, I mean in neighborhoods the function is unbounded, right? And we have no other problems, so it is integrable over each interval which doesn't contain those points, then we understand this improper integral as the sum of several improper integrals. So you see, what means improper integrals in general? We look at our function and we try to understand where our function is unbounded, where it has problems, right? So then what we have to do? We have to consider separately each of those points from each side. So every term here contains only one problem. What I mean by problem? For example, here, look. There is only one point x2 such that in a neighborhood of that point the function is unbounded, right? So it means we need to consider that integral as a limit as upper limit tends to x2 from the left hand side. Analogously for other. And let me finish our example 3, to unify both. What is about integral from 0 to infinity dx over x power alpha? Look, according to this general definition, we have two problems, 0 and infinity, right? So we need to split it into two integrals. In fact, you can choose other point, not necessarily one, just 2, 3, doesn't matter. Some points between 0 and infinity, nothing else. And now look, this integral converges only for alpha less than 1, right? The second integral converges for alpha greater than 1. We cannot have both inequalities together, right? At least one of them is not satisfied. Hence, what it means? At least one of those terms is not defined. It diverges, right? At least one of them. Hence, our improper integral diverges in any case. So this diverges for arbitrary alpha. That is how to proceed if we have several problems. Now, from now on, in theory, I'll consider only problems in the upper limit, so I'll not consider problems with lower limit because they are similar. So everything will be formulated only for limits as b tends to capital B. Now look, so the main object for us now is that one. which we consider as limit as b tends to b minus integral from a to b f of x dx. So, from that point of view, improper integrals are limits of a function. Which function? Integral with variable upper limit, right? That is integral with variable upper limit. So we need to consider limits of functions. Okay, for limits of functions, we know there is a Cauchy, how it is called? Cauchy criterion, right? So, what is Cauchy criterion? So, the limit to be f of x dx exists if and only if for arbitrary epsilon greater than 0 there exists delta greater than 0 such that for all b greater than a, sorry, delta greater than 0, okay, for all, now it's, okay, let me write like that, b1, b2 in a neighborhood of b minus, right, u minus delta minus of b, we have difference, modulo of difference between integral from a to b2 f of x dx minus integral from a to b1 f of x dx is less than epsilon. So what is u delta minus of b? U delta minus of b is what? That is b minus capital B minus delta b if b is a finite number, and let's say a, in fact it should be delta b, delta infinity, if b equals to plus infinity. So neighborhood of capital B from the left side. So that is Cauchy criteria for the function of b, and hence it gives, okay, I think how it is called, Cauchy criterion, yeah. So criterion, sorry, yeah, criterion. For limit of a function. For limit of a function. So what I wrote here was Cauchy criterion for the limit of a function. Now I can use properties of integrals, and it gives, let me write, two Cauchy criterion for two improper integrals. So first, Cauchy criterion for integral from a to plus infinity f of x dx. Suppose f is Riemann integrable over ab for all b a less than b. The improper integral from a up to plus infinity f of x dx converges if and only if for arbitrary epsilon greater than 0 there exists okay, let it be capital A. Capital A is not good. Let it be delta greater than 0 such that greater than A such that for all b1 b2 such that delta less b1 less b2 we have modular integral from b1 up to b2 f of x dx less than epsilon. That is Cauchy criterion for such integral. And analogously I'll formulate Cauchy criterion for second type of improper integral. So Cauchy criterion for integral from a up to capital B f of x dx. B is finite. Suppose f is Riemann integrable for any interval AB, where B is between A and capital B. The improper integral from A to capital B f of x dx converges if and only if for arbitrary epsilon greater than 0 there exists delta greater than 0. Oh, sorry. Okay, let it be like that. Such that for all b1, b2, capital B minus delta less b1 less b2 less capital B, we have modular integral from b1 up to b2 f of x dx less than epsilon. So once again, to those Cauchy criteria are precisely immediate consequences of Cauchy criterion for the limit of a function. So you consider definition of improper integral. Definition says that the improper integral is the limit of a function. Which function? Integral with variable upper limit. Integral with variable upper limit is a function. So you consider limit of a function, hence you apply Cauchy criterion for the limit of a function, and then what you have to do? You need to take into account additivity property of integral. That's all, to write down this one. That's all. So that is simply reformulation of Cauchy criterion for limits of functions. And now it gives an assertion about convergence of improper integrals. And how it works? Let me formulate next. Yeah, comparison theorem. Comparison theorem. Okay, look, before to formulate, you see, those assertions are very similar, right? Here you should consider something near capital B, and here near infinity, roughly speaking. So in future, I'll not formulate in both situations, but only in one. So theorem 1, comparison theorem. Suppose fg are integrable over interval ab for all b greater than a. And 0 less or equal f of x less or equal g of x for all x greater or equal than a. If integral from a to plus infinity g of x dx converges, then integral from a to plus infinity f of x dx converges as well. If integral from a to plus infinity f of x dx diverges, then integral from a to plus infinity g of x dx is divergent too. So roughly speaking, look, we compare two functions. One of them is greater than another, right? Then, if the integral of a greater function converges, then integral of smaller function converges as well. And opposite side, integral of smaller function diverges, then integral of greater function diverges as well. So, why? Because, recall, integral is area under the graph, right? So, one function, look, one function f of x and we have another function g of x, right? So if area under g of x is finite, and it means integral of g of x converges, then the area under f of x is finite as well, right? And conversely, if area under f of x is infinite, then area under g of x is infinite as well, right? Because area under g is always greater or equal than area under f. That is the meaning of this assertion. But formally, to prove it, we need to refer to Cauchy criterion. So, proof. Look, for example, let us proceed with first part. Integral converges. Then, according to Cauchy criterion, for arbitrary epsilon, there exists delta greater than a such that for all b1, b2 which satisfy delta less b1 less than b2, we have inequality integral from b1 to b2 g of x dx less than epsilon. Then, by our inequality, what we can deduce? Look, integral from b1 to b2 f of x dx is less or equal, that is non-negative, less or equal than integral from b1 to b2 g of x dx. And we know it's less than epsilon, right? So then what it means? I underline what I need now. The integral is non-negative and less than epsilon. What it means? It means everything what is written in Cauchy criterion for f, for convergence of integral of f, is satisfied, right? So, immediate consequence of Cauchy criterion. So, Cauchy criterion, again Cauchy criterion, says integral from a to infinity f of x dx converges. Now, opposite direction. In opposite direction, we should consider opposite, an assertion opposite to Cauchy criterion. So what it means? Negation. So what is negation of Cauchy criterion? Yes, you are right. This is indeed like two policemen in some sense. In some sense, yes, definitely. But not precisely. We cannot refer just to policemen. No. Okay, then, yeah. So what is negation of Cauchy for f? Cauchy criterion is not satisfied. Negation, take negation. What it means? There exists epsilon, so let me write like that. Integral from a to infinity f of x dx diverges. So, negation, what it says? There exists epsilon greater than 0 such that for all delta greater than a, there exists b1, b2 such that delta less b1 less b2, and the opposite inequality integral from b1 to b2 f of x dx greater or equal to epsilon is satisfied, right? Look, f is non-negative, so we don't need to use modulus here. And from our condition, it follows that integral from b1 to b2 g of x dx greater or equal than integral from b1 to b2 f of x dx, and that is non-negative. And in fact, I can write like that, non-negative, right? And also, you see, hence, modulus of b1 to b2 is also greater or equal than epsilon, right? Because, okay, I'll write like that firstly, integral from b1 to b2 f of x dx, and it is greater or equal than epsilon. And once again, all quantifiers together underlined, they say that integral from a to plus infinity g of x dx diverges. That is how Cauchy criterion works, and it gives us a very powerful tool, in fact, to study the convergence. For example, look, if you know somehow what can you say about integral from 1 up to plus infinity sine squared of x over x squared dx. It converges. Why? Because sine squared of x is non-negative, less or equal 1 over x squared, right? And integral from 1 up to plus infinity dx over x squared converges. Yeah? So, by comparison theorem, our integral converges as well. So you see, almost immediate. And that is indeed works very often, very often. This comparison theorem. You see, the proof is very simple, just apply Cauchy criterion, nothing else. And simple inequality, nothing else. But it works quite often, quite often. You see, here I could compute the integral explicitly, right? But it's impossible for that one. You cannot find primitive. So, but nevertheless, you know, it has a sense. It has a sense. It is finite. So you can use it as a number. Okay, I think it's a good point to stop now. Right? Thank you very much.